Hey everyone, and welcome back for another deep dive. Today we are going to be talking about something
Oh, yeah.
pretty wild. We're going to be talking about neutron stars
Mm-hmm.
and the sounds they make.
Yes.
And we're looking at an article all about this.
Yeah.
It says that neutron stars collide and ring like a cosmic bell, revealing hidden secrets.
That's right.
And it's kind of a weird concept to wrap your head around. Like, how does a tuning fork analogy
Right.
work with something as massive as a neutron star?
Yeah. It is interesting to think about.
What secrets can we unlock by listening to their ring? But before we get too far into that,
Yeah.
just for anyone who might be joining us for the first time, what exactly are neutron stars?
Neutron stars are the collapsed cores of massive stars that have exploded as supernovae. They're incredibly dense.
So they're like the leftovers of a huge star that went supernova.
Exactly. So imagine taking something way bigger than our sun.
Bigger than our sun.
Yeah, much bigger, and squeezing it down to the size of a city, like 12 kilometers across.
Wow.
That's a neutron star. And a teaspoonful of that stuff would weigh billions of tons here on Earth.
Billions of tons just in one teaspoon. Yeah, okay, that's dense.
Yeah, really dense.
But it's not like we could just go grab a teaspoonful, right? I mean, how do we even figure out what they're made of?
Right, that's where the collisions come in, when two neutron stars spiral into each other.
Spiral into each other.
Yeah, they actually orbit each other, sometimes for millions of years.
Wow.
And they slowly get closer and closer together. When they finally collide, it releases a huge burst of energy in the form of gravitational wave.
Okay, so I remember gravitational waves, those are like ripples in space-time.
Exactly, like ripples in a pod, but instead of water, it's the fabric of space-time itself that's rippling.
Wow. And we can actually detect those ripples.
Yes, we have these incredible detectors like LIGO and Virgo. They use lasers to measure these tiny distortions in space caused by the gravitational waves.
So we can actually, like, hear the collision, but how does that tell us what the neutron star is made of?
It's not just the initial crash that's important. The real key is what happens after the collision. There's this thing called the long ringdown.
The long ring down.
Yeah, basically the remnant of the collision, which is usually a single, even more massive neutron star, emits gravitational waves that gradually fade out.
Okay.
But as they fade, they become more refined, settling into a dominant frequency. It's like a cosmic tuning fork.
Wait, so the neutron star keeps vibrating after the crash, and we can actually detect those vibrations.
Precisely. That's the amazing part. We're not just detecting the collision itself. We're detecting the dying breaths of the newly formed object, its final vibrations as it settles into a stable state.
Okay, I think I'm starting to see where this is going. The sound of the ring down tells us something about the star itself.
That's right. The material that the neutron star is made of directly affects how it vibrates, how it rings.
Okay, but how do we go from sound to actually knowing what's inside? Like, what's the connection there?
Think about tuning forks. A fork made of steel sounds different from one made of aluminum, right? Each material vibrates at a different frequency.
Oh, yeah, I get that.
Same thing with neutron stars.
So the frequency of the long ring down
Yep,
depends on what the neutron star is made of, like a fingerprint.
exactly. It's like the star is singing a song that tells us about the deepest secrets.
That's so cool. But hold on, how do we even know this ring down thing exists? Is this something we've actually observed?
Well, not directly observed yet. Our current gravitational wave detectors aren't quite sensitive enough to pick up the post-murder signal, but researchers have been running incredibly detailed computer simulations of neutron star mergers.
Simulations?
Yeah, we can actually simulate these incredibly powerful events on supercomputers.
Hold on, wait. You're saying we can simulate something as intense as a neutron star collision?
We can. It's pretty amazing, actually. The amount of computing power involved is just mind-blowing.
Okay, but like, what do these simulations even look like? Are we talking giant explosions and all that?
Not explosions in the visual sense. Remember, we're dealing with gravitational waves here.
Right.
But these simulations are insanely complex.
Yeah, I bet.
They have to take into account things like general relativity, nuclear physics, and all sorts of crazy physics that we're still trying to understand.
So it's not like watching a movie. It's more like...
It's more like crunching numbers and looking at data visualizations, but the insights we get are incredible.
Okay, so what have we learned from these simulations?
Well, for one thing, they've shown us that this long ring down is a consistent feature of neutron star mergers. So even though we haven't observed it directly yet, we're pretty confident it's happening.
Okay, that makes sense. So it's not just a theory. It's something that's backed up by, some pretty powerful simulations.
Exactly. And these simulations are based on something called equations of state.
Equations of state, what are those?
Well, imagine you're trying to bake a cake.
Okay, I like where this is going.
But you've never seen flour before, right?
Yeah.
It's a key ingredient. But you have no idea how it's going to behave when you heat it up, mix it with other ingredients and all that.
Right. It could turn into a brick or be all fluffy.
Exactly. So the equation of state for flour would tell you how it expands, how it interacts with other ingredients, and ultimately whether your cake is going to be a fluffy masterpiece or a dense brick.
Okay, so the equation of state is like a blueprint for how matter behaves under, like, extreme conditions.
Got it. And just like there are different types of flour for different cakes, there are different equations of state for different types of neutron stars. The problem is we don't have a perfect recipe yet. We're still figuring out how matter behaves under the insane pressures and densities found inside these stars.
And that's where the long ring down comes in. It's like listening to the cake baking.
Laugh, that's a great way to put it. By analyzing the frequency and other characteristics of the ringdown, we can compare it to the predictions of different equations of state and see which ones fit best. And the more data we have, the more we can refine those recipes and understand the inner workings of these stars.
So it's like we're trying to reverse engineer the universe's most extreme cake recipe. Amazing. But even if we get the recipe right, are we still limited? We can only hear these collisions, we can't see them. Doesn't that make it harder to figure things out?
It's true that gravitational waves give us a different perspective than traditional astronomy, which relies on light. We can't see the collision in the same way that we see a star through a telescope.
Right.
But it's not necessarily a limitation. It's more like having a whole new sense to explore the universe with.
So we're getting a whole different kind of information.
Exactly. Information that we wouldn't be able to get from light alone. It's like, imagine trying to understand a symphony just by looking at the sheet music.
Oh, yeah.
You wouldn't really get the full picture, would you? You need to actually hear the music.
Right, to experience it.
And that's what gravitational waves are doing for us. They're letting us experience the universe in a completely new way.
I guess that makes sense. So by combining what we hear with what we see, we can get a more complete picture of these cosmic events.
Absolutely. And what we're learning is already changing our understanding of neutron stars. There's evidence to suggest that they might contain some truly exotic forms of matter.
Okay, now you've really got my attention. Exotic matter. What do you mean by that?
We're talking about stuff that doesn't even exist here on Earth. Things like strange matter or superfluidity.
Strange matter. Superfluidity. I'm going to need you to explain those.
Sure. So strange matter is a hypothetical type of matter that's thought to be even denser than the matter found in neutron stars. It's made up of strange quarks, which are these fundamental particles that we don't normally see in everyday life.
So it's like a whole different level of matter.
Exactly. And superfluidity is another really bizarre phenomenon. It's a state of matter where there's zero viscosity.
Zero viscosity. What does that even mean?
It means that a superfluid can flow without any resistance. Imagine pouring honey from a jar.
Yeah, it's pretty thick.
Right, it's pretty thick and gooey. It flows slowly because it has a high viscosity. But a superfluid would just flow out instantly, like water, but even more smoothly.
Wow. Okay, so are you saying that the insides of a neutron star might be like a superfluid made of strange matter?
It's possible. We don't know for sure yet, but the conditions inside neutron stars are so extreme that it's definitely within the realm of possibility. And if we can detect the long ring down, it could give us the evidence we need to confirm these theories.
So we're talking about stuff that's totally mind-blowing, like physics-breaking stuff.
Yeah, it's pretty wild stuff. We're really pushing the boundaries of what we know about the universe.
Okay, I am totally hooked. But we're just getting started. We'll be back in a bit to continue our deep dive into the sounds of neutron stars. So could studying these sounds actually, like, help us understand things like dark matter?
Oh, that's a good question.
Or even, like, unlock some new energy sources we haven't even thought of?
It's definitely possible. The conditions inside neutron stars are so extreme that they could create particles we've never even dreamed of.
Whoa.
And we're talking about densities and pressures that are just unimaginable here on Earth.
Yeah.
And that could lead to the formation of completely new types of matter.
Okay.
New particles that could have all sorts of implications for particle physics and cosmology, and even potentially new energy sources.
So we're not just studying neutron stars. We're like studying the fundamental building blocks of the universe.
Yeah, exactly.
When we study this stuff.
It's all connected.
Okay. I'm definitely hooked. But before we get too far down the rabbit hole here, I want to go back to these equations of state for a second.
Sure.
I'm still kind of fuzzy on what they actually are.
Yeah, I can see how that can be confusing.
So, like, they're basically recipes for extreme matter.
Uh-huh.
Right?
Well, yeah, I mean, that's a good analogy. They describe how matter behaves under extreme pressure and density.
But how do they, like, actually work? Like, what do they look like?
Okay, so imagine you're trying to bake a cake, right?
Okay, back in cakes. I like it.
You've never seen flour before in your life.
Okay.
You know, it's like a key ingredient.
Yeah.
but you have no idea how it will behave under heat and pressure.
Right.
So the equation of state for flour would tell you things like how it expands, how it interacts with other ingredients, and ultimately whether your cake will be a fluffy masterpiece or a dense brick.
I see. So the equation of state is kind of like a blueprint for how matter behaves
Exactly.
under extreme conditions.
It tells you the relationship between pressure, density, and temperature for a given material,
Okay.
and how those properties change as the conditions change.
So just like there are different types of flour for different cakes, there are different equations of state for different types of neutron stars.
Exactly. And the problem is we don't have a perfect recipe yet for neutron star matter. We're still trying to figure out which equation of state best describes how matter behaves at those insane densities.
So that's where this long ringdown comes in.
Yes.
It's like listening to the cake baking
That's a great way to put it.
to figure out which recipe is the right one.
By analyzing the frequency and other characteristics of the ringdown, we can compare it to the predictions of different equations of state and see which ones fit best. And as we get more data from gravitational wave observations, we can refine those equations of state and get a better understanding of the inner workings of these stars.
So we're trying to reverse engineer the universe's most extreme cake recipe by listening to its gravitational baking sounds.
Laughs.
That is just crazy to think about.
It's pretty mind-blowing when you think about it that way.
But okay, even if we figure out the recipe, isn't it still limited? Like, we're only hearing these collisions, not seeing them. How can we be sure we're getting the whole picture?
It's a good point. Gravitational waves give us a different perspective than traditional astronomy, which relies on light. We can't see the collision in the same way that we see a star through a telescope.
Right.
But it's not necessarily a limitation. It's more like having a whole new sense to explore the universe with.
Oh, okay.
Like, imagine trying to understand a symphony just by looking at the sheet music.
Oh.
You wouldn't really get the full picture.
Well,
You need to actually hear the music.
Yeah, to experience it.
Exactly.
Okay, so it's like adding a whole new dimension to our understanding.
Exactly. It's like we've been exploring the universe with one eye closed for centuries.
Right.
And now we finally open the other eye.
That's amazing.
And we're seeing things we never could have imagined before.
So by combining what we hear with what we see, we can get a much more complete picture
Absolutely.
of these cosmic events.
And what we're learning is already changing our understanding of neutron stars. There's evidence to suggest that they might contain some truly exotic forms of matter.
Okay, wait, back up for a second. You keep saying evolution of the universe.
Right.
What do you mean by that? Like, are neutron stars actually affecting how the universe changes over time?
They definitely play a role. For one thing, they're responsible for creating some of the heaviest elements in the universe.
Really?
Yeah. When they collide, they release a huge amount of energy and material, which can seed the surrounding space with elements like gold.
Gold comes from neutron stars?
It can. Also platinum, uranium.
Wow.
All sorts of heavy elements.
So the gold in my ring
could very well have come.
Could have come from a neutron star collision.
From a neutron star collision billions of years ago.
That's incredible. But how do they actually create these elements? Like, what's the process?
It's a process called nucleosynthesis.
Okay.
During the collision, protons and neutrons are forced together under incredible pressure and temperature, forming heavier and heavier nuclei. It's like a cosmic forge, creating the building blocks for planets and stars and even life itself.
So these collisions are not only shaping the composition of the universe, but they're also creating the ingredients for everything around us.
Exactly. It's a beautiful cycle, isn't it?
It really is. And we can learn about all of this just by listening to these sounds.
That's the power of gravitational wave astronomy. It's giving us a whole new way to understand the universe.
That's amazing. But you mentioned earlier that our current detectors haven't actually observed this long ringdown phase yet.
That's right. The signals are just too faint for our current technology to pick up.
So what's next? Are we just waiting for, like, better technology?
We are working on developing more sensitive detectors. Projects like the Einstein telescope are specifically designed to catch these faint signals from the long ringdown. And when those telescopes come online, it's going to be a game changer. We'll be able to study these mergers in unprecedented detail. Who knows what we'll find?
I'm already getting chills. So we're like on the verge of a golden age of neutron star astronomy.
Absolutely. And it's not just about neutron stars either. By studying these extreme environments, we're pushing the boundaries of physics as a whole.
So all this talk about, like, exotic matter, extreme conditions, what are some of the biggest unanswered questions about neutron stars right now? What are scientists most eager to figure out?
One of the biggest mysteries is what happens at the very core of a neutron star.
The core?
Yeah. We know the pressures are so intense that even atoms themselves are crushed.
Whoa.
But what exactly does matter look like in that state? Is it just a sea of neutrons? Or is there something even more exotic going on, like a soup of quarks? Or maybe even some completely unknown form of matter?
So the sound of the long ring down, could it actually tell us what's happening at the core?
It could. Different core compositions would produce different ring-down patterns. It's like using sound waves to probe the interior of the Earth,
Oh, yeah.
but on a much grander scale.
That's incredible. Okay, but gotta ask, what about the practical implications of all this? Like, are there any real-world applications for this kind of research?
Well, for one thing, it's helping us develop better models of gravity. Neutron stars are some of the most massive objects in the universe.
Yeah.
So they provide an extreme testbed for Einstein's theory of general relativity.
So by studying how these stars warp spacetime, we can, like, check if Einstein got it right.
Exactly, and so far his theory has held up remarkably well.
Good job, Einstein.
But there are still some mysteries that general relativity can't fully explain, like dark matter and dark energy. So who knows, maybe by studying neutron stars, we'll find clues that lead to a new understanding of gravity itself.
Okay, that's huge. So we're not just talking about understanding neutron stars. We're talking about understanding the fundamental forces
Right.
that govern the universe.
It's all connected.
Wow, no pressure or anything.
Bucks, no pressure at all. But that's what makes this field so exciting. Every discovery opens up new possibilities, new questions to explore.
Well, I think we've given our listeners plenty to ponder today. This has been an incredible deep dive into the world of neutron stars.
It really has. These objects are truly fascinating, and I think we're only just beginning to scratch the surface of what they can teach us.
Before we wrap up, is there anything else you want our listeners to keep in mind? Any final thoughts?
I'd just say keep looking up, keep asking questions, and never underestimate the power of curiosity. The universe is full of wonders, and we're just beginning to explore them.
I love that. And who knows, maybe one day we'll be able to hear those cosmic bells ourselves. Thanks to the work of scientists like you. Thanks so much for joining us today. And to our listeners, as always, thanks for diving deep with us.